Welcome to the AI Checkpoints. Before we dive in, just a quick disclaimer. This content is generated by AI. Today, we're really getting into something critical and maybe a bit misunderstood in the world of large language models. It's called context rot.
Yeah, it's this phenomenon that explains why even the really powerful LLMs can sometimes stumble on tasks when you give them super long inputs. It really impacts their reliability, their performance.
So, our mission today is to kind of unpack this idea, look at some pretty surprising research findings, actually, and give you some practical insights. How can you manage your LLM context more effectively?
Exactly. Think of it as a shortcut, maybe, to understanding why just throwing more context at a model isn't always the answer. It's not always better performance.
Okay, so where are we getting our info today?
We're drawing heavily from the researchers over at Chroma, specifically their scientific advisor Anton and researcher Kelly. They've got some great stuff on their YouTube channel.
Right, I saw those. Behind the research, context rot. And another one, context rot, how increasing input tokens impacts LLM performance. Definitely worth checking out on the Grumman channel.
And we're also looking at a really sharp paper analysis of Chroma's work by Yannick Kilcher. He's got a video on his YouTube channel covering it, adds some valuable extra perspective.
Okay, great. So context rot, it sounds, well, it sounds bad. What exactly is it? Why should we really be paying attention?
It's a good question because it hits right at reliability. Basically, context rot is just this degradation, this drop-off in an LLM's performance as the input context gets longer and longer.
Even if the model says it can handle like a million tokens.
Exactly. That's the surprising part. It can technically process it, maybe, but it doesn't mean it will do so reliably or accurately. You often see this consistent downward trend as the context size balloons.
Right, because we hear all the hype, don't we? These new models, huge context windows, near perfect scores on the needle in a haystack benchmark.
Yes, the needle in a haystack. It was, a decent first step for benchmarking.
But
But the Chroma research really highlights that, well, it's often just too simple. Kelly from Chroma explains it's usually just a basic retrieval task. You hide a random fact, the needle, in a ton of text, the haystack, and the model finds it.
and the catch, as Yannick Kilcher also pointed out, is that it often boils down to like a direct word match, right? A lexical match.
Precisely. So if the question is what was the best running advice, and the needle says the best running advice was, the model just spots those matching words.
It doesn't really need to understand anything deeply. It's more like a glorified Chromel plus F sometimes.
Pretty much. It's not testing real comprehension or reasoning in complex situations.
Okay, so the Chroma researchers decided to push beyond that. They designed tougher tests.
Yeah, they introduced more subtle challenges to see how these models perform under, let's say, more realistic pressure. And the results were quite revealing.
Like what? What did they find?
Well, one key thing was ambiguity. How does the model handle it when the answer isn't spelled out perfectly clearly? They actually varied the semantic similarity, how close in meaning the needle was to the question, using cosine similarity.
Okay, give me an example.
Sure. So a high similarity, easy needle might be the best writing advice was to write every week. For the question, what was the best writing advice? Easy match.
Okay.
But a more ambiguous one, needing more inference, could be something like, one thing people don't know is I write every week. It's a useful habit. Started back in college when a guy in my English course suggested it.
Ah, I see. The core information is there, but it's phrased differently. The model has to connect the dots.
Exactly. And what they found was, well, pretty fascinating. Models actually handled the ambiguity okay with short inputs,
Right.
but as the input length grew, their ability to handle that same ambiguity just plummeted. Our performance degraded way faster.
So the models can do it. They have the capability, but not when it's buried.
Yeah.
It's like trying to hear a whisper in a really noisy room.
That's a great analogy. The sheer volume of surrounding, potentially irrelevant text just overwhelms its ability to pinpoint and process that slightly fuzzy target.
Okay, that makes sense. But real-world text isn't just long. It's also messy. What about things that look like the answer but aren't quite right?
You're talking about distractors. Yeah, that was another crucial element they tested, and something Yannick Kilcher really emphasized too. These are bits of info that are topically related, maybe semantically similar, but don't actually answer the question.
Right, like asking for advice from a classmate, and the text includes similar advice from a professor.
Exactly. Kelly and Anton called them adversarial elements in the haystack. They're designed almost to mislead the model.
And how did the models cope with those?
Not well, especially as context grew. They found even one distractor caused performance to degrade. Add 4 distractors, and it got significantly worse, particularly with those longer contexts.
Wow. And that's huge, right?
Yeah.
Because real documents, code bases, transcripts, they're absolutely full of stuff like that. Related, but not quite the answer you need.
Absolutely. It shows how easily models can get sidetracked or confused by near misinformation when dealing with large inputs. The more distractors, the harder it gets.
Did they look at the haystack itself? Like, does the type of text surrounding the needle matter?
They did. They tested how the topic of the haystack, say, Paul Graham essays versus technical RCIF papers, affected things, especially when the question needle pair was either aligned with the topic or completely different.
And what did they find there? Did a relevant haystack help?
You'd think so, but they also did something really interesting. They varied the structure of the haystack. Sometimes it was coherent text, like essays. Other times, they literally shuffled the sentences to make it random and incoherent.
Okay, that sounds weird. Why?
Well, here's the counterintuitive part. Sometimes the models actually performed better when the needle was placed in the random incoherent haystack.
Better? How does that work?
The speculation is that if the surrounding text is just noise, completely jumbled, the model might not waste processing power trying to make sense of it. It sort of gives up on the context, allowing the distinct needle to stand out more easily.
Huh. So a messy context might sometimes be less distracting than a context that looks coherent but is actually full of those near-miss distractors.
Potentially. It suggests context isn't processed uniformly or linearly. The model's attention seems to work in complex, sometimes unpredictable ways.
Okay, let's shift gears a bit. What about conversations? Like chatbots or assistants that need to remember things over a long interaction.
Yeah, that's a huge use case. They use the long Aliva benchmark for this. It involves conversations up to 500 messages, which is, around 120,000 tokens. Massive.
And what was the comparison?
They compared performance using the full chat history context versus a super condensed version, maybe just 300 relevant tokens, summarizing the key points needed for the task.
Let me guess the condensed version 1.
By a long shot. The results were really stark. Models did significantly better on the condensed version for tasks like knowledge updates, figuring out timing over the chat history, things like that.
And so just dumping the entire chat history into the prompt. Bad idea.
It seems so. It really demonstrates that you can't just assume shoving everything in works reliably. A focused, curated context beat the full fire hose approach, even for the exact same task. More isn't better.
Okay, this next one, this experiment really, it really surprised me. They tested something incredibly basic, right?
Oh, the replication task, yes. It's almost unbelievable. They asked models to just replicate a list of repeated words, like apple 100 times, but with one slightly different word, maybe apples, slipped in somewhere.
And the instruction was just copy this exactly.
Exactly. Replicate exactly what is given. Something a simple script could do perfectly in milliseconds.
The multi-billion parameter models failed.
Astonishingly, yes. Even with fairly short inputs, just a few thousand tokens, they struggled. Models would generate random stuff, repeat the word way too many times, or sometimes just refuse.
Refuse? What, like give an error?
Sometimes citing things like copyrighted material or inconsistency. It was bizarre behavior for such a simple, deterministic task.
That's wild. What does that even mean about how they work?
It really underscores a critical point. You cannot treat these LLMs like traditional deterministic computers, even for basic stuff. Their whole auto-regressive nature, predicting the next word based on the previous ones, combined with internal biases we don't fully understand, makes their behavior unpredictable.
Even if you set the temperature to 0, trying to force deterministic output.
Even then, as Anton from Chroma put it, you really can't predict how it'll perform until you actually run it. It's still fundamentally a probabilistic system, a black box in many ways.
Okay, so wrapping our heads around all this.
Yeah.
What are the big takeaways for people actually building things with LLMs, or even just trying to use them effectively?
I think the number one takeaway is that huge context window number you see advertised. Don't take it as a guarantee of reliable performance across that entire length.
Right. Your effective, reliable context window might be much, much smaller in practice.
Precisely. And as Kelly from Chroma said, as the task got more realistic, these models perform worse. Often, it's not the task itself that's impossibly hard. It's how the model uses or fails to use the context unevenly.
Which leads us to this idea of context engineering. Sounds fancy, but what does it mean practically?
It's essentially about optimization. How do you maximize the relevant information you give the model while minimizing the irrelevant noise and those tricky distractors?
It's about being smart with the input, not just throwing everything at the wall.
Exactly. It's an optimization problem. As Yannick Kilcher discussed too, getting reliable performance often depends on how well you engineer that context.
Okay, so how do we actually do that? What are some strategies?
Well, one common one is summarization, especially for things like multi-step agents or long chats, instead of feeding the entire history back in each time.
You summarize the key points from the previous steps.
Right. You distill the important bits into a shorter, more focused memory or state. It keeps the context relevant and manageable.
Makes sense. What else?
Retrieval augmented generation, or RAG, using vector databases. This is great for static knowledge, like documentation or FAQs. You store the info externally.
And then just pull out the most relevant snippets for the current query.
Exactly. You retrieve only what's needed when it's needed. It's usually faster, cheaper, and keeps the context clean. But, you need to experiment with your retrieval setup, embedding models, chunking strategy, how many snippets to pull to get it right for your specific data.
So there's no magic bullet, no single setting that works everywhere. It's about testing and iterating for your specific use case.
Absolutely. What works brilliantly for one application might fall flat in another. Experimentation is key.
Looking ahead, did the Chroma folks speculate on how this context rot problem might eventually be solved? Is it fixable?
They did engage in some wild speculation, as they called it. Anton seemed a bit more optimistic, suggesting maybe more compute power and figuring out how to mitigate biases from the pre-training data could fix it.
And Kelly?
Kelly seemed to think it might require more fundamental changes, perhaps to the model architecture itself, to really understand and control how they process information internally.
So the jury's still out on whether it's an inherent limitation of the current transformer architecture or just like a really stubborn training artifact we can eventually overcome.
Yeah, Anton wondered if it relates to pre-training biases or maybe even the finite capacity of the attention heads themselves. Maybe they can only effectively focus on so much information at once, especially relevant information.
Lots to explore there for researchers. Investigating open source models, designing better benchmarks that reflect real-world messiness, not just length.
Definitely. There's a lot more work to be done by the community to really nail this down.
Okay, so let's try to sum this up. The big message seems clear. LLMs might boast huge context windows, but just filling them up blindly is asking for trouble.
Right. You can easily run into inconsistent, unreliable performance. More tokens doesn't automatically mean better results, and sometimes it means much worse.
So effective context engineering, using smart techniques like summarization, like retrieval, isn't just a nice extra. It's becoming essential.
It really is. It's a crucial skill for anyone working seriously with these models. You have to be intentional about the context you provide.
Because understanding context rot really means understanding that how you present information to an LLM matters just as much as what information you give it.
Absolutely. It's about the strategy, the curation, not just the volume.
So the next time you're building an LLM app, maybe pause and ask, am I being smart about my context here?
Or am I just letting context rot creep in and potentially undermine my model's performance? It's a question worth asking.
Well, we hope this deep dive into context rot has sparked some thoughts and maybe given you a few aha moments. Hit like and subscribe if you like the content. See you next time.